In this video, we will talk about a common error folks make when evaluating improper integrals. So I'm going to look at an example to illustrate this. Let's evaluate the integral from -2 to 1 of 10 over x to the 6th. So I first want to do this incorrectly. So I'm going to talk about an incorrect solution. So I see this integral. Okay, so I see this integral from -2 to 1. And with 10 over x to the 6th, I can take the antiderivative of that if I first write it as 10, bring x to the 6th up to the numerator. So that'll be x to the -6. And then use the reverse power rule. So we'd get 10 x to the -5, and then divide by that new power. So divide by -5. And then vertical line, 1, and then -2. And now I'm going to simplify a little bit. 10 over -5, that is -2. And let's bring x to the -5 to the denominator. So we get this over x to the 5. And then vertical line, and then we have the 1 and the -2. So now plugging in 1, we will get -2 over 1 to the 5 minus, now plug in -2, we get -2 over -2 to the 5. So simplifying now, the first term is just -2, and then double negative becomes a positive. And then with the 2, and then divided by this -2 to the 5th, that becomes 2 over, and then -2 to the 5th is -32. And this can be simplified to -1 over 16. And if we get a common denominator with this and simplify it, we end up getting -33 over 16. So it turns out this is wrong. So to see why, let's look at the graph of y equals 10 over x to the 6th of our function. So I'm going to draw this in. Okay, so let's scroll it down a little bit, and let's draw in this graph. So the graph of 10 over x to the 6th has one part of it over here in this first quadrant, one symmetric part over here in the second quadrant, and we are evaluating the integral from -2 to 1. So starting at -2 and then ending at 1. So that corresponds to the area of this part of the graph, as well as the stuff on the other side of that vertical asymptote, which is this part of the graph. But just by looking at this, there is no way that this area should be negative, because this whole region is above the x-axis. No way. This area should be negative. And we got a negative answer here. We got -33 over 16. So the question then is, why didn't this work? So I want you to pause the video for maybe 45 seconds and see if you can figure out either what was wrong about our computation or the correct way that we needed to approach this. So 4, 3, 2, 1, pause that video. Pause it for 45 seconds to think about, why didn't this work computationally, and what the correct way that we need to approach this is. All right, so hopefully you did that. Hopefully you paused it for about 45 seconds to think about that. So the answer is that this integral from -2 to +1 of 10 over x to the 6th dx, it's this function 10 over x to the 6th, it's discontinuous somewhere in this interval. We see that it has this vertical asymptote at 0, which makes this an improper integral. So because it's an improper integral, that means doing what we did, which was just FTC, Fundamental Theorem of Calculus, Part 2, doesn't apply. So just taking the antiderivative, plugging those bounds and subtracting, that doesn't work because it's an improper integral. We have to be more careful. So this was improper because our function was discontinuous at 0, and that's relevant because 0 is in this interval that we're talking about, -2 to 1. Alrighty, so one of the key takeaways from this is now when we evaluate integrals, we must first check if the integral, and I'm just going to abbreviate it int, if the integral is improper. Because with this problem, we didn't check if it was improper first. We kind of just dove into a computation, but it turns out that computation doesn't work because this was an improper integral, and this is not the way that we're supposed to handle them. All right, so now let's do this correctly. Alrighty, so here is our integral one more time, and I want to do a correct solution. So the discontinuity is somewhere in the middle of this interval from -2 to 1. So since that's the case, since it's discontinuity, I'm just going to abbreviate discont for discontinuity, since its discontinuity is in the middle of the interval, we need to split this into 2 pieces. So we'd split it at that discontinuity. So we have to go from -2 to 0 of this function, 10 over x to the 6th dx. And then plus another integral where I pick it up at 0, the discontinuity, until 1 of 10 over x to the 6th dx. And each of these integrals involves that discontinuity point at x equals 0. So each of these integrals is an improper integral in its own right. So each of these is improper because they each have 0 as an endpoint, and 0 is a number that makes 10 over x to the 6th discontinuous. Okay, so to evaluate both of these, we're going to need to use limits. So I'm going to pick one of them to just begin with. So I'm going to pick the second one. But it doesn't matter if I wanted to pick the first one to begin with. I definitely could. All right, so let's evaluate that second integral from 0 to 1 of 10 over x to the 6th dx. So I'm going to highlight this just so I can clearly see, well, which one is it out of these two that I'm working with. Okay, so we need to evaluate this integral. So I'm going to replace the discontinuity point, which is 0, with t. So I'll get the integral from t to 1 of 10 over x to the 6th dx. And I need to take a limit. So the limit as t is approaching, should it be from the left or from the right? Well, I can draw a number line to help me remember. My interval is from 0 to 1. And to approach 0 within this interval, we have to be approaching it from this side if we're staying in the interval. So we're approaching 0 from the right side. So I'll say t is approaching 0 with a little plus sign. That means it's approaching it from the right. Okay, so what does this equal? We get the limit as t approaches 0 from the right. And we actually did the antiderivative of 10 over x to the 6th already. So we got that was -2 over x to the 5. And then I have to plug in 1 and t. So doing that, we get the limit as t approaches 0 from the right. If I plug in 1, we get -2 minus And now if I plug in t, we get negative 2 over t to the 5, which simplifies, and I get the limit as t approaches 0 from the right of negative 2 plus 2 over t to the 5, because we have that double negative. All right, so we evaluated the antiderivative. We've plugged in our bounds, our limits of integration. At this point, we have this limit. And as we've seen before, with limits, we typically want to begin by just trying to plug in the number. So let's just plug in this case, it's t equals 0. Let's not even worry about the fact that it's from the right just yet. And try to plug that in and see what happens. Okay, so doing that, this equals negative 2 plus 2 over 0 to the 5. So with this fraction, the denominator is 0, which is going to make that undefined. But on the top, we have a non-zero term. We have 2. So we have a non-zero term on the top. On the bottom, we have 0. And if we think back to the previous calculus class, or if that was Math 30 for you, back when you saw things of the form non-zero over 0, our strategy to deal with these was to take one-sided limits. But our limit that we are doing here, t is approaching 0 from the right, is already one-sided. But this is already one-sided, which means we get to just focus on this specific side. All right, so what does that look like in practice? So when we're writing what this is, when we plugged in, we could actually just focus on this side and get negative 2 plus 2 over. And on the denominator, I'm going to write 0 with a little plus sign in the exponent. So this is some notation that we can use to say that this term is close to 0, but bigger than it. That's what putting that little plus sign in the exponent means, that we're on the right side of 0. If I think about on the number line, we are on the right side of 0, which is this side, which means we're a little bit bigger than 0. Okay. So that gives us negative 2 in the front plus 2 over. So if you raise this number, which is close to 0, but a little bit bigger than it, which means it's positive, to the 5th power, it's still going to be close to 0, and it's still going to be a little bit bigger than it, because it's still positive. So I put a little plus sign there still. Okay, so this becomes negative 2 plus. And then if you divide 2 by something of this form, something that's really close to 0, but a little bit bigger than it, that overall fraction, this overall fraction is going to be super, super big. It's going to be huge. So that is approaching infinity. And negative 2 plus infinity, well, that is just infinity. Okay, so I'm going to highlight this term and highlight this infinity to show that, oh, those were the same. So why is that? This is something that we would have talked about in the previous calc class or Math 30, but let's remind ourselves, why is something like 2 over something really, really small, really close to 0, but a little bit bigger than it, why is that infinity? Well, the reason for that is this is something of the form 2 over something really, really small. So imagine I have a fraction like 1 over 1 million. That is something really close to 0, but bigger than it. So if you take 2 and you divide it by a fraction like this, that's the same thing as multiplying by the reciprocal. So you get 2 times the reciprocal, 1 million. And when you reciprocal that thing, it makes it really huge. This is huge now. And that's why it ends up being infinity. The smaller I make this denominator, when I reciprocal it, the bigger that is. And that's what makes it go to infinity. Okay, so that means that this integral, if I scroll it up to the top again, Remember, we split up the original problem into these two integrals, and we focused on the second one, and now we know that the second one diverges. Let's write that down. Since one of these integrals diverges, we evaluated the second one and we got that it diverges, that automatically means the original one, our original integral, diverges as well. So when we split up an integral into two pieces, if either of those pieces diverges, the original one diverges. So that's nice. We didn't have to do both of them. Just doing the second one and getting that it diverges gave us the answer automatically. It does turn out that if you were to evaluate this first integral, it would also diverge. That doesn't always happen though. Sometimes when you split up an integral into two pieces, like we did here, it might happen that one of them converges and one of them diverges. And in that situation, if you were to pick the one that diverges first and show that it diverges, it would be quicker because then you could stop and not have to evaluate the other one. But we don't always know that beforehand. Well, we may get a little bit better at recognizing that with experience, but for right now, we're just in the introductory phases of learning how to evaluate these improper integrals. So we'll get better at that with time. All right, so in the next video, we are going to look at another example. In fact, in terms of our goals for this section, we have finished our third goal, which is evaluating some type 2 integrals. That's where our function becomes infinite somewhere on the interval because of a vertical asymptote, because of an infinite discontinuity.